I sure hope that everyone's having a great day today. I'm Lawrence Snyder, and I'd like to welcome you to the all-new High Performance Fundamentals YouTube channel. So question, what do you need to know to design, fabricate, install, and test an automotive electrical circuit, or the entire automotive electrical system for that matter? In the first video of this video series, we're going to cover terminology, we're going to cover Ohm's law, we're going to cover Watt's law, we're going to cover the digital volt ohm meter, or also known as the DVOM. The end goal here is to provide you with a well-rounded knowledge base so that you can confidently create a safe and properly functioning electrical system. Alright, so with that being said, we're going to get the ball rolling with Ohm's law. Now stay with me here. Don't switch off just yet. There's going to be some math, there's some calculations, there's some formulas, but in order to create a properly functioning electrical circuit, you have to know them. Now, the good part is that it's simple math. Everybody's got a calculator in their pocket when they're carrying their phone around these days, and it is very basic, very simple math. The hardest part really is knowing how to find the values. How do you find for amperage, for example? And then plug in those numbers for those values into the equations. Once you find the values and you plug them in there, it's very simple math. And I'll take you down that path of determining exactly what you need to know to create that circuit. Whether it be the size of the fuse, the size of the gauge of the wire, the type of relay, what circuit breaker you want to use, when do you use a circuit breaker, when do you use a fuse, all these different things, what's safe, what operates properly, what do you need to know there? I'm going to run through all of that. In this video series, we're going to go through every bit of that. But to start off with, we've got to get through these equations. They're pretty quick, they're pretty simple. You can obviously pause this video and write these down or take a picture of it with your phone or do whatever it is you want to do and just keep them, for future reference. They're not that difficult. We just got to get over the terminology so we understand what exactly, the formula is talking about. What are the figures we need to plug into these formulas to get an accurate result. So let's get started with Ohm's law, and we'll get these out of the way, and we'll move on to something a little bit more interesting, okay? Alright, so to start with Ohm's law. What is Ohm's law? Ohm's law is electromotive force is equal to the current intensity multiplied by the resistance. Okay, so electromotive force, current intensity, resistance. Alright, so that is when you're trying to find for electromotive force. If you already know the current intensity and the resistance, you multiply the two together, it'll give you your answer, which is electromotive force. Okay, so then you can just take that equation and break it down further. If you're trying to find for electromotive force, we know E equals I times R. If you're trying to find for current intensity, then you would take electromotive force divided by the resistance. If you're trying to find for the resistance, you would take electromotive force divided by the current intensity. Okay, so like I said, pretty simple math, division, multiplication. It's just a matter of knowing what are those figures. I mean, what does that terminology mean? All right, so I'm going to break it down a little further for you. And the reason I'm going to do that is because if you're using a digital volt ohm meter to find these values, right, you're not going to see electromotive force on your digital volt ohm meter. It's not going to be on there. You're not going to see it. Okay, you're not going to see something that says current intensity, right? You won't even see something that says resistance. It'll be replaced by something else. But those numbers are there. Those figures are there. You just got to break it down a little differently. So here's what I'm going to do. So here's what I want you to know. So electromotive force, okay, is actually expressed, quantified, and measured as voltage. Okay? Current intensity is expressed, quantified, and measured as amperage. All right, very good. Resistance is expressed, quantified, and measured as ohmage or ohms. All right, so we're going to break it down. We're going to change this around a little bit and make it something that's a little bit easier to understand, a little bit easier to wrap your mind around when you're plugging in the numbers. Basically, is what I'm going to do here. So this is what I've been doing for over 40 years. This is how I do it. It works perfectly fine. There's nothing wrong with doing it this way. It's just it makes it a little simpler. Anytime you can make electrical circuits simpler, you're doing the right thing. All right, so let's break it down. Let's change this around. So instead of E, let's make it V. Instead of I, let's make it A. Instead of R, let's make it O. Because these are the values you're actually going to find on your volt ohm meter, digital volt ohm meter. Volts, amps, and ohms. That's what you're actually going to find. And they're going to replace electromotive force, current intensity, and resistance. We're going to replace those. So let's do that. So V equals A times O. V being voltage, okay? A being amperage, O being ohmage. All right, now, voltage is going to be expressed and quantified and measured as volts. Okay, so for example, you could ask somebody like, what's the voltage in that circuit? Or you can say, hey, what's the volts? Either one would be accurate, okay? Amperage, okay, is expressed, quantified, and measured as amperes or amps. So if I said to you, what's the total amperes in that circuit, or what's the amperage, or what's the amps, all of that would be accurate, okay? Just kind of abbreviating it, bringing it down a little bit, okay? Ohmage is resistance, okay? So ohmage is going to be expressed, quantified, and measured as ohms, okay? And this is ohms. All right, so we'll get to what all this means here in a minute, but I just want to give you an idea. So let's just change this around a little bit. So voltage equals amperage times ohmage, all right? Okay, if you want to, and that's if you want to find for voltage. If you want to find for amperage, amperage is going to equal voltage divided by ohmage. Like I said, you're going to be finding these figures with your digital voltmeter. And then, of course, ohmage would then be equal to voltage divided by amperage. Okay? So like I said, V is for voltage or volts, A is for amperage, amperes or amps, O is for ohmage or ohms. All right? And that's basically what there is to know about Ohm's law. Okay? Now, obviously it gets more technical than that, but this is what you need to know. We can break it down further. We can really get into it. We can even talk about who created it, right? But there's no sense in all that. This is what you need to know when it comes to Ohm's law. Okay, so that's going to be basically looking for voltage, amperage, and ohmage. That's what we're looking for. That's what we need to know when creating a circuit. Now, let's move on to Watt's law. So what's Watt's law? Watt's law is power equals voltage times current intensity. Okay? All right, so power. Nothing on here says power, I promise you, right? All right, so as a matter of fact, nothing on here is actually going to say watts. Nothing on here says watts, right? Because it's a calculation. You have to calculate it. All right, so, but we know that we've already talked about this. So P is power, but it's going to be expressed and quantified as wattage or watts. Okay, so P is watts or wattage. All right, V is voltage. We've already discussed that. It's going to be expressed, quantified, and measured as volts. Okay, current intensity is, as we've already expressed, is amperage. It's going to be expressed and quantified and measured as amperes or amps. So Watt's law is P equals V times I. Once again, simple multiplication. And then from there, if we want to find for power, we'll take voltage times current intensity. If we want to find for voltage, we'll take the power or the kilowatts, well, let's just say power for now, divide that by the current intensity. If we want to find the current intensity, we'll take power and divide that by voltage. Okay, so like I said, breaking it down just a little bit further, P is power or wattage, V is voltage, I is current intensity or amperage. So once again, let's modify that formula just a little bit. Let's make it a little bit easier to understand, okay? Just a little bit. And like I said, because, anytime you can replace terminology like current intensity, right, it becomes more helpful. Or P for power, which is, a measurement of force, right, or work, right, which is great. So let's break it down a little further. Let's change this around and make it W equals V times A. So P is power or wattage, and V is voltage, and current intensity is amperage or amps, right? So W equals V times A. So once again, W, V, A, wattage is expressed and quantified as watts. Voltage is expressed, quantified, and measured as volts. Amperage is expressed, quantified, and measured as amperes or amps. So once again, just like over here, it's very simple multiplication and division, not very difficult at all. Wattage will equal voltage times amperage. Okay, voltage, if you want to find for voltage, will equal wattage divided by amperage. If you want to find amperage, then you take wattage divided by voltage. Okay, so those are your equations, right? Now, don't get me wrong. Now, I'm not going to tell you that that's all there is to know. That's absolutely not true. But these are your basic equations. Ohm's law and Watt's law. You have to understand what it means. You have to understand what they are. You have to understand where you get the figures. You have to plug them into the equation before you can ever start determining what you need to do to create that circuit. Once you have the raw materials, the wire, the connectors, the fuses, the actual load itself, let's say a fan or a pump or, whatever it might be, an ignition coil, whatever it might be, pick it, the horn, some sort of a load, okay? Once you have all the parts and components in place, now you got to say to yourself, well, what size fuse do I need? What size wire do I need? What type of relay should I use? Should I use a circuit breaker? How do you know? right? What do you need to know so that the circuit operates properly, right? To where your headlights aren't dim, they're actually bright. And when your fuel pump doesn't run slow, it runs at normal speed. It's not unsafe. The harnesses don't get hot. You have no chance of a fire, which is a real thing that can actually happen. It does happen, as a matter of fact. Okay, so we've got Ohm's law out of the way, Watt's law out of the way. Now we got to talk about, okay, we have to find those values, okay? And that's where your digital volt ohm meter comes in. Digital volt ohm meter, something like on this line, right? Basically, that's what you're going to be using, right? Little rotary dial, bunch of different selections, what have you. But you're going to be using your DVOM to find these figures. And there's a lot of stuff here about DVOMs on this board for sure. And we're going to go over all of it. We're going to go over some of this kind of quickly. Just going to touch on it because that's really not what this video is about. But we are going to talk about volts, amps, and ohms to a decent amount. We're going to get into that. Okay, so volts on your voltmeter is going to be the letter V, right? You can either select DC or AC voltage. Okay. Amps is A. You can, and from your amp scale, you'll find that you might be able to select 20 amps, 10 amps. There's different selections. We'll go over that, but amps is on there. This may also be determined through the use of a inline ammeter or an inductive ammeter, and we'll go over that too. All right, and then you have ohms. Now, ohms in most cases is going to be expressed by, that's the Greek letter omega, right? And that's the symbol used for ohms, and that's what you're going to see. Whether it's, milliohms, or ohms, kiloohms, or mega ohms, whatever it might be, that's the symbol you're going to see. It's the Greek letter for omega. All right, so now you got to think about, well, okay, that's cool, but let's say that you don't really understand. I mean, what is voltage? What is amperage? What is resistance or ohmage? What is that, right? How do you wrap your mind around that? How does one affect the other? When you're trying to figure it out, like you can plug the numbers in, you can get in the result, but do you really understand what's going on there? Okay, so what I want to do is I want to do what I call, this is my own thing, right? I've never heard anybody do it quite like this, but it is I feel like an easier way to understand what each one of those values really means. All right, and I call it the water tower analogy, right? I'm probably going to become known as a water tower analogy guy. I feel pretty sure that may happen. But whatever, that's how when I was first trying to understand this, literally 40 years ago, 45 years ago, it was confusing, especially when we started crunching the numbers and we got into series circuits and parallel circuits and series parallel circuits and resistances and some of the way the wire schematics are drawn. It can be really confusing. It really can. So you've got to understand from the beginning, what are we talking about, right? Okay. So let's go ahead and get into this water tower analogy. Now, don't make fun of my drawings, because that's not very nice, you can laugh all you want, but just don't laugh at me, I guess. Okay, so that's my water tower analogy, right? Driving down the highway, look over the side of the highway, you see this big old water tower sticking up in the air, driving through town, there's one in the middle of town, or whatever there might be. Right? Okay, so we got 3 different water towers here, right? 3 different scenarios. One of them is either half full or 100% full, 50% or 100%, half or full, right? And on the bottom down here, we have a pressure gauge, right? Over here, we got another one, it's 100% full, right? We have a pressure gauge here and here. We have a restriction, and we have a flow meter, okay? Now, like I said, we're going to relate all this to voltage, amperage, ohmage. We're going to relate all that. Over here we have another one that's 100% full, but instead of it being closed, sealed at the end, this one's actually flowing. Okay? You have the same 2 pressure gauges, one before the restriction and one after, and we have the same flow meter in line. As you can see, the readings, they're changing, right? So I want you to be able to wrap your mind around when I say voltage, when I say volts, when I say amperage, when I say amps, when I say ohmage or ohms. I want you to be able to kind of just get a rough idea, like a feel for what that really means, okay? So we're going to talk about stored energy, all right? Now, in this scenario right here, or in this scenario, either one, right, when you're 50% full, you have 50 pounds per square inch measured on the gauge. Now, this is not an accurate depiction of how much water. I didn't calculate how much the water weighs or how long the tower is or how tall the tower is. placement of the gauge. I didn't do any of that. This is just for just a rough idea, just get you thinking, right? So if I fill this water tower halfway up, let's say I develop 50 pounds per square inch, right? So now I have 50 psi, 50 pounds per square inch, plus a lot of volume. So I have a lot of stored energy, right? Potential energy, just sitting there, just ready to go, right? Well, let's fill it up. Let's double it. Let's fill it to 100%. Well, now I have 100%. Now I have 100 psi, right? So now I have this big reservoir with even more water, right? Even more, twice as much. Well, I've doubled my pressure, right? The mass of the water, the physical weight of the water, is pushing down on the water column and creating a higher psi. Much the same way as if you go diving or you dive into a swimming pool, you go to the bottom of the pool, you start to feel pressure. Well, the reason is that inside your body is atmospheric pressure. You got your holding your breath. Okay, so now you have atmospheric pressure sealed inside your body. Go down into the water, the column of water above you is pushing in on you, right? Literally, it's greater than the atmospheric pressure that's inside your body, and you feel that pressure. The further down you dive, if you dive into a lake or the ocean, the further down you go, it gets worse, right? Because the physical weight pushing on your body, or in this case, on this water column, gets greater and greater as I add more and more volume. Okay, so now I know we've got potential energy, we've got stored potential energy. We have half as much as we do here, right? Okay, that makes perfect sense. So how is this voltage? Well, voltage, I want you to understand voltage as pressure. Okay, and here's what I mean by that. Let's say you have a battery sitting on the table here, and it's just sitting there. It's fully charged, right? Let's say it's a 12-volt battery. You measure it, it's 12.6, 12.8 volts, somewhere in that order. It's fully charged. It's just sitting there, right? We all know that there's energy there, right? We know this, right? Can you see it? No. Is it doing anything? No. But it's ready to go. It's just busting at the seams. It wants to get out of there, right? It's because it's ready to go. So think of voltage as pressure. Here I am. I'm stored energy. I'm looking for a way out of here. I'm looking for a path. Let me out of here. I want to go, okay? Let's just think about it that way. So let's think about voltage as pressure, all right? So in that scenario, let's say that this was a 6-volt battery, and that's a 12-volt battery. It has twice the potential energy, right? Let's just look at it that way. 6 volts, 12 volts. Instead of this being a pressure gauge, we'll make that a voltmeter, a volt gauge, right? So here we would see 6 volts, or we would see 12 volts, right? So that's what I want you to think about. Stored energy under pressure, all right? So a battery is stored energy under pressure. If you think about it like that, it's easy to think about, okay, well, that makes sense. I have an energy source in storage waiting to be utilized, okay? Much the same way as this water tower is waiting to be tapped into and come to your faucet at your house. You turn on the faucet, out comes the water under pretty substantial pressure, okay? Same basic theory, right? Potential energy, a storage of energy waiting to be utilized. So think of voltage as pressure, okay? And the greater storage, the more pressure. 6 volts, 12 volts, 6 volts, 12 volts, right? Instead of a pressure gauge, PSI gauge here, we would have a voltmeter. It's really the difference. So think of a voltmeter as a pressure gauge, measuring electrical pressure, okay? All right, so that's my water tower analogy. Now let's move on. Let's go to some different scenarios. Now, let's add a flow meter, okay? We're going to measure the actual flow coming through the column from the water tower, okay? But we have the ends closed, all right? The ends closed. The flow, 0 gallons per minute. Gallons per minute, 0. Of course, the end's closed. There's no flow, right? Now, what is a flow meter? That's an ammeter, an amp gauge, right? When you're measuring electrical flow, the rate or volume of flow through an electrical circuit, you're measuring amperage or amps with an ammeter or an amp gauge. Ammeter is more technical, but amp gauge is oftentimes used to replace ammeter, but ammeter is more technical, more correctly. The more correct terminology is ammeter. All right, so ammeter or flow meter. Flow meter for water, ammeter for electrical current. It measures flow. In this case, it's closed. So we're full, nothing's happening. We're creating pressure, but we're not utilizing it. It's just sitting there. Now I've added a restriction, and I want you to know this. So we have a gauge here and a gauge here, and we have a restriction in the middle. When you cap the end, the pressure is the same. Okay? Why wouldn't it be? 100 psi here, comes through the restriction, builds up pressure here, 100 psi. 100 psi, 100 psi, 0 flow. Nothing's happening, right? Now here's why you have to test electrical circuits while operating. Okay, when you want to know exactly how much amperage is being drawn or the voltage drop in a circuit, it must be functioning. Now here's why. All right, scenario number 3. Same 100% full tower. Of course, it's getting less and less as it flows. It's getting less, so 100, 95, 90, 85, it's going down, down, down. But it begins to flow. It just began to flow just right now. All right, we pop the end open. Water starts flowing. But now we have a restriction. But we do have flow. So now our flow meter, instead of reading 0, is reading 200 gallons per minute. Now keep in mind, we have thousands of gallons of water up here under great pressure, right? So like I said, I haven't calculated these numbers to say is that an accurate number, how much volume is up here? Absolutely not. This is just an analogy for you to get your mind wrapped around what's going on. So now we're flowing. All right, so we have opened the end, we're flowing, right? That water is flowing, but it's going through a restriction. All right, so we're slowing it down, we're necking it down a bit, right? The restriction is obviously a smaller orifice or a smaller size pipe, let's say, than the outlet pipe or the inlet pipe. So it's a restriction, it's kind of in the way, right? Okay, so now we've gone from 0 gallons per minute to 200 gallons per minute, right? So basically we have flow on our flow meter. If this was an ammeter, we would be showing, instead of 0 amps, we would be flowing, let's just say, come up with a number, 20 amps, right? Because now we have electrical current flow. It's flowing, right? So we're measuring flow. If we stop, no flow, right? The ammeter would read 0. So, but it's okay, so what do we have over here, right? So we have 2 pressure gauges, right? And what we're measuring here is what's called pressure drop, right? Okay, so I'm going to get into that a little deeper. But, so here's 2 gauges. The difference between the 2 is the pressure drop. All right, we pop the end open. Theoretically, we're not measuring it. We're not actually there measuring it right now. But theoretically, you're going to have something around the order of 0 to maybe, let's just come up with a number. Let's say 5 psi. You may have some pressure there. So why do we have pressure there, at all? I mean, basically it's wide open. It's just flowing, right? No restriction. It's just flowing on by. But you got to keep in mind the amount of volume we have here, right? The actual force pushing through this pipe, right? And the fact that since it's still flowing through a pipe, there may be some small restriction, whether it's the diameter of the pipe or maybe it's just the friction of the walls of the pipe as the water flows through it. There still might be a restriction, and there might be enough of a restriction to actually produce a little bit of pressure. Maybe not, right? We're not there, we're not testing it, we haven't calculated it, but it's a possibility. Now I want you to know this because let's say that same scenario, right, with an electrical circuit. This is our battery, right? This is our resistance, right? And this is the ground path back to the battery. Okay, so this is your ground, right? That makes up a circuit. You have on a battery will be your positive side of the battery. Your negative side of the battery would be here, right? Return path to the battery. So basically positive to negative, positive to negative, positive to negative, positive to negative. Now, I'm not going to get very technical about that. I know we can get into polarity when you start talking electrical polarity. It's actually negative to positive. But in an automotive system, when you're placing fuses, you're putting in grounds, you're creating a circuit, you're going to be putting it in such an order that positive through the fuse, to the load, to the ground, or back to the battery. That's the way you're going to create the circuit, positive to negative. You don't create it the other way around. Let's create the negative side and eventually we'll create the positive side. That's not how you do it. Okay, so that being said, now we have, instead of a flow meter, we now have an ammeter, right? Like what I was saying earlier. So since we're flowing, right, since electrical current is flowing, the ammeter is going to start to read. 10 amps, 20 amps, whatever it may read, depending on the circuit, depending on the restriction, right? So now we know that an ammeter measures flow, right? So once again, our 12-volt battery, 12 volts or 6 volts, this is our 12-volt battery, right? And we're measuring, since this is a volume of water, we're measuring pressure differential. If this was a voltmeter, we'd be measuring what's called voltage drop, where we actually check voltage here and then here, and the difference between the two is our voltage drop. In this case, the difference between the two is your pressure drop, okay? Now, in terms of water flow or liquid flow, that would be called your differential pressure. Pressure drop is known as differential pressure or your delta P, okay? Just for the guys out there who are technical, right? Pressure drop is going to be known as your differential pressure or your delta P, all right? That's not really relevant to this discussion, but I just want to make that clear. So in this case, instead of that being, once we said before, instead of that being a pressure gauge, that's going to be a voltmeter. instead of that being a pressure gauge, that's also going to be the voltmeter, right? So we're going to measure the resistance across that circuit by voltage drop, okay? So since there's a restriction in flow, we'll have greater voltage here than we have here, okay? So that would be voltage drop. The restriction is going to be ohmage, all right? The restriction is going to be measured and quantified as ohmage in an electrical circuit. In a water circuit like this, right, you're flowing through there, the restriction might be measured in surface area. For example, 12-inch diameter pipe, 6-inch diameter pipe, right? So the actual surface area across the pipe differs greatly. And then, of course, you get even more technical than that. You get into what they call discharge coefficient, and that's also not pertinent to this discussion. But the restriction is a restriction. It's basically going to be determined initially on surface area, and then from there additional calculations. But as you can see, a restriction in flow to that water. If this is an electrical circuit, that's going to be the resistance. The resistance could be a resistor. It could be the load. A load being a light bulb. It could be an electric fan motor. It could be a fuel injector. It could be, any type of load, the starter motor, whatever it might be, the load in the circuit. When you're wiring up the circuit, what are you wiring up the circuit for, right? It could be the amp for your radio in your car. Whatever it might be, that's the load, right? And that's going to have a set amount of resistance. And there might even be more resistance in line, right? You have to calculate all of that. And in another video, we'll get into calculating resistance. Series circuits, series parallel, and parallel circuits. We'll get into that, we'll talk about that. We'll actually go back to our water tower analogy to try to make those circuits more understandable. Okay, but nonetheless, what I want to get across here is, what's voltage? Voltage is pressure, okay? Stored energy. What is current intensity? Current intensity is amperage or flow, actual flow, right? What is ohmage? Ohmage is resistance or restriction, okay? Like I said, in this case, we have a stored energy reservoir. We've opened that stored energy reservoir. We're allowing flow to occur. We have created a restriction, which is going to create a pressure drop, right? And also, we're now going to see actual flow through our flow meter at 200 gallons per meter, 200 gallons per minute. I'm sorry. But nonetheless, as you can see, right, this is an active circuit, right? Whether it be water or voltage, it's active. This is inactive, right? Same gauges, but as you can see, no activity, right? Inactive, closed, no flow. This one's flowing. In electrical circuits, we say the same thing. Is the current flowing or is it not flowing? That's what we actually say. You can talk about all the technical literature or mumbo jumbo, whatever you want to call it, right? But is there current flowing in the circuit, right? That's what I would say. If somebody asked me, that's the question I'm going to ask you. So basically, like I said, test your circuits with the current flowing, with the circuit active, right? Actually, current flowing. Test them in that way. When you're creating circuits, you can test them various ways, and we're actually going to get into that just a little bit. I'm going to go ahead and move on from here. We're going to get into the DVOM some, and then I'm going to get into a little bit of how to make some checks with your DVOM, and then we're going to wrap it up. All right? Okay, so let's move on to the digital volt ohm meter. All right? Basically, like I shown you earlier, digital volt ohm meter. This is an OTC brand, very capable. I bought this in 1992. I still have it. It works flawlessly. I've basically had to replace some fuses in it, the battery over the years, put new leads on it several different times. But I've had it going on 33 years. It works absolutely fine. It works for me. It's always been great. I bought a lot of accessories with this when I bought it. Amp clamps, thermal couples. We'll get into that a little bit. Different types of leads, different things, inductive pickups. But what I'm getting at here is that I've had this for 33 years. You definitely want to make sure that your digital volt ohm meter is of quality, okay? I don't know if the OTC 500 is still a good DVOM. I have no idea. I can tell you that when they made it 33 years ago, it was great. Nowadays, basically, everybody compares themselves to Fluke. You make your own decision. There's a lot of really good DVOMs out there. It doesn't have to be a Fluke, but, the reality of it is that most everybody does, they compare themselves to Fluke. They really do. They tend to be the most expensive, or in my opinion, anyhow. But they are a quality unit, and a lot of industries, not just the automotive industry, they rely on Fluke. So, make your own decision. This OTC has been great for me. I bought this, like I said, in 1992. I paid $550 for it in 1992. So it came in a big kit. It's not just a DVOM. There's a lot of attachments that went with it, but it was very, very expensive at the time, but it's been great. So, like I said, make your own decision on that. I don't really have a recommendation. Do some research. There's some good ones out there for sure. All right, so we need to move on to digital volt ohm meters, because when we're creating a circuit, we have to know certain values like we had already discussed. We have to be able to find those values. We have to be able to measure them, right? We have to have a device to allow us to measure them, so we can record those values, all right? So the three biggest ones, and I've kind of got it lined out here, in importance to me. Over the years, what have I used my DVOM for the most, right? 1, 2, 3, 4 through 6, 4, 5, and 6, these three, 7, 8 through 10, you switch them around, and that's probably number 11. In an automotive application, you rarely will use that, but in household AC current, you're trying to diagnose your AC system at home, which I do, you're going to need to know how to measure capacitance, right? Absolutely. It's a common failure, something you're going to need to know to do. My meter can do it, and I do use it for that. And it has come in, quite handy, doing home applications. But in a car application, it's been years since I've used it. But it's most of the capacitors, condensers, they're internal to your electronic components. Not something you're going to be testing unless you actually take the component apart, unsolder it, take out the capacitors and measure them. That's not something you're going to be doing. I mean, rarely, if ever, right? So that definitely comes in last on my list of importance. But by all means, Ohm's law, Watt's law, it's a top 3, right? And sure enough, you're going to be checking volts, amps, and ohms on a regular basis. If you're doing diagnostic work, you're testing circuits, you're creating circuits. Those are the 3 big ones, 100%, right? So depending on the voltmeter that you have, it may have, like this is what's on my voltmeter and what I'm used to seeing, right? I've used a lot of different types of voltmeters over the years, DVOMs, digital volt ohm meters. I've used a lot of different types over the years, and this is what you tend to see, okay? So basically we're going to talk about VA and the Greek symbol for omega, or ohms, right? These are the 3 we're going to talk about the most. We'll touch on some of these others and may get into that in greater detail in a later video. But for right now, let's hit on the top 3 and then we'll just touch on these, okay? So basically volts, you're going to need to select on your volt ohm meter, digital volt ohm meter, whether whether you're measuring DC, direct current, or alternating current. The majority of the time, you're going to be measuring direct current. There are times in automotive applications that you will measure alternating current. It's not all that often, but you will at times. And usually if you're following a diagnostic path, it'll tell you to select AC or alternating current on the scale on your meter. Not only AC voltage, but also what scale. It'll actually tell you that in the diagnostic information or diagnostic flow chart. So you kind of will know. But you also learn over the years, what is an AC voltage generator, what circuits have AC voltage, you'll learn these things over time. So basically we're talking about direct current, so voltage, DC voltage, or DCV, direct current voltage, all right? You're going to see on your meter, you're going to see a small m with a V, small k with a V. Those are the ones you're going to use the most. Now, you can go on beyond that, right? But in automotive applications, low voltage DC applications, it could be cars, trucks, boats, motorcycles, trailers, RVs, all low voltage, 12 volt, 24 volt, even 48 volt at times, especially now with hybrid vehicles. But nonetheless, so small m is millivolts, volts, and kilovolts. All right, that is 1/1000th of a volt. That is 1 volt. That is 1,000 volts. All right, so for example, if you hooked it up to the circuit and it said 1 kV, that means you're measuring 1,000 volts DC, right? That's not something you're going to run into very often, I promise you, but it is possible to see some pretty high voltage. On the other hand, if it says 500 MV, right, it takes 1,000 millivolts to make a volt. So if you have 500 millivolts, you have a half a volt. 0.500 volts, 1/2 of 1 volt is 500 millivolts. You will see that. Right? If you're on the millivolt scale, that's how it's going to read. If it says 40 millivolts, that's 40 1,000ths of a volt. That's going to read 40 millivolts, right? Or 0.040 volts, 40 millivolts, right? If it's kilovolts, like I said, so let's say you're at 500 volts and you're on the kilovolt scale and it says 0.500 kV, that's half of 1,000, 0.5 is going to be 500 volts. If you were to switch back to your volt scale probably doesn't go as high as 500 volts. It's going to have a much lower range than that. So you may get on if you get into a situation where you're measuring voltage or amperage or even ohmage, if you're on the wrong scale, a lot of times it'll come up like OL. You see OL, it means out of limits, right? Your scale is wrong, right? And there may be something else, depending on your meter. I can't tell you about every meter and exactly what it's going to display because I haven't used every meter that's out there. I mean, I haven't. I've used a lot of them. I have 100% have not used them all. I do not know what they all display, right? You must follow your information guide that's going to come with your DVOM, right? It may be different. And there's going to be several things here that I'll talk about, and yours might be slightly different, but as long as you know the scales and you follow the instructions, there's a lot of examples. As an example, there are a lot of examples. So nonetheless, your DVOM and your instruction manual, may be different than others. Just follow along and use it as a reference guide. Okay. All right. So like I said, direct current voltage, alternating current voltage. Now, one thing I want to throw out there to you guys, in most cases, direct current voltage, DC voltage, right? So DC voltage, in most cases, is not going to harm you, all right? Now please, understand this. If you're working on an EV, an all-electric vehicle, you're going to be running into 600 volts DC. That will kill you, 100%. Right? 800 volts DC, 300 volts DC, 340, 320, 360, whatever it might be, right? That will kill you. That will kill you as soon as I'm standing here. And if it doesn't kill you, it'll kill you eventually. If you get electrocuted by high direct current voltage to the point where, let's say it knocks you out, you literally fall out for a second, and you come to. You can actually develop I don't even know the technical term for it, but it's called blood poisoning, and in 24 to 48 hours later, you'll be dead. Right? So if you get electrocuted by high DC voltage, get yourself to the emergency room immediately, tell them what happened. Right? Get yourself there, let somebody else get you there. If you're working on high voltage, DC voltage like that on electric vehicles, make sure that somebody's there. Never work alone. Never, ever, ever work alone. Right? Something bad happens, nobody's going to be there to save you. If there is somebody there to save you, make sure they understand that if you were electrocuted, it's not okay for you to be like, oh, I'm good, I ain't worried about it, because 2 days from now you might be dead, right? You got to get to the emergency room. Now, when does it become dangerous, right? If I'm working on an older model vehicle, or even newer model vehicles for that matter, and it has a 12-volt DC system, listen, I guess theoretically it's possible that it could hurt you, but it's never in my lifetime, nobody I've ever known, it's not going to hurt you, right? Same as you take a 9-volt battery, take a brand new 9-volt battery and touch it to your tongue, it's like, dang, it'll shock you a little bit, but it didn't hurt you. So now we're going from 9 volts to 12 volts, right? Okay, well, it might tingle, there's situations, where you might feel it, but is it going to kill you? No. So at what level do you need to get worried, right? Well, at about 50 volts DC, you need to start thinking about it. You need to really be thinking like, So for example, let's say you're working on a 48 volt system. Well, that's less than 50, so you're good. Well, when the car's running and it's charging that 48 volt battery, it's going to be between 54 and 58 volts. Somewhere in that area, certain applications may differ. But let's say 54 to 58 volts. That's definitely more than 50, right? So if you had a charging cable, from the starter generator or the alternator, going back to the 48 volt battery, and you happen to touch one end of it and then put your hand on the engine, right? That's a bad path to have electrical current flow up one arm through your heart, out the other arm, right? I wouldn't do it, right? It's 48 volt system. I got it. I hear you, but don't do it, right? Don't do it. It gets up in anything for me 48 volts. I start getting real cautious. I really do. Anything a 48 volt system or greater, I start really getting nervous. I work on them. I do what I got to do. And I've never been hurt in any way, shape, or form, but I'm very, very careful. 12 volt systems, less cautious, put it that way. All right, so I just want to make that clear. 50 volts, when you check in for that. All right, so basically your voltmeter, you check for voltage, whether it be DC or AC. You're basically just going to use two probes, very simple. One's red, one's black, right? this is your positive, this is your negative, boom, boom, no big deal. Your DVOM will show you where they go, which one is which, right? Okay, negative, positive, ground, hot side, right? Very simple. So when you're measuring amperage, right? So amperage is going to be a little different. All right, so how do we measure current flowing through a wire? There's different ways of doing it, right? So for example, this is a Mac brand, right? This is an old inline, right, or in series ammeter. So literally, what you do is you wire this into the circuit. So one lead comes in, one lead goes out, right? So instead of you going, let's say, from the battery to a fuse and then to the rest of the circuit, you would go from the battery to here, then from here to the fuse, and you would be in line with the circuit. So now you literally have opened the circuit and you are now in line. So all the current has to flow through the ammeter, right? That's an inline ammeter, right? There's no doubting what you're going to see because all the current is flowing through here, right? You basically broke the circuit open, stuck this in series like this, right? And the ammeter is going to read what's flowing through it, right? So that's an inline ammeter, right? Okay, so from there we have inductive ammeters. Here's one made by Pico, right? This one is good for 60 amps, right? It's an inductive ammeter. This one is from OTC. This one can go up to 2,000 amps, okay? This inductive. Two other types of inductive ammeters, much simpler, right? This actually is this one's for doing starter current. This is an old, I've had these for a very long time. I've been doing this for a long time, right? And this one measures up to 600 amps. This one is labeled as an alternator current, and this one goes up to 100 amps. Now, if you work on alternators, you know that nowadays alternators can be a lot greater than that, 160 amps, right? But it goes 100 amps. So this is good. Doesn't matter what it says on it. It's good up to 100 amps. This one's good up to 600 amps. And you look on the back here, you'll see this little groove right here. That lays on the wire, just like this, right? And this one's exactly the same way. It lays over the wire, just like that. Current flowing through the wire, right, is measured by the inductive ammeter. This is inductive. This is inductive, right? This style, let me get my hand out of the way, right? This style, right? All inductive. These go around the wire, right? Open that up, slide the wire right through it, right? Like that. Clamp onto the wire or over the wire. Same thing here, it's much larger. Then again, we might be putting a very large cable through here to measure up to 2,000 amps. So once again, this is an OTC brand. I've had it for 33 years, never failed me, right? Very simple. So if it's in line, well, one more. Let me go one more. Here's your DVOM. Now these one over here I showed you, not these ones, this one. This can go up to 60 amps, right? This can't. And this has an internal fuse, okay? So on one end of it, it can go up to 20 amps. And on this end, it can go up to 400 milliamps or 0.4 amps. Very, very low flow, very low current circuit, low amperage, but up to 20 amps, okay? Inside, there's a fuse. If you exceed that value, that fuse will blow. It protects the meter, okay? I've blown them many times. You just, whatever, you forget, you got it on the wrong side, you're going to check 15 amps, and you got it on the milliamp side, the fuse is gone immediately. So they'll blow and just replace them, no big deal. So this is an inline also, just like the other one I showed you. You will literally wire inline, just like this. So you'll take your red or your positive lead, stick it onto your 20 amp scale, keep your ground lead or your negative lead on your ground terminal, or what they call common, right? And select over here. We'll go over and select 20 amps, right? Now our meter is now an inline, just like the other one was, ammeter with a fused circuit. So inline and inductive, all right? So the beauty of inductive is that an inductive ammeter, you don't have to open a circuit. You basically all you have to do is operate the circuit. That's great. So how does that work, right? Okay, so let's use the small one. This one, it says made by Pico, also a very good brand, right? It's made by Pico, wraps around the wire. It's much smaller than the other. It's made for much lower current circuits, right? So it gets a lot closer to the conductor. Okay, so what does it measure? All right, so here's what you got to know. When current flows through a wire, through a conductor, the wire is the conductor. When current flows through the wire, it creates a magnetic field around the wire. Okay, as the current increases, that magnetic field increases. Well, this actually has the ability to measure that magnetic field. Okay, so greater current intensity, greater amperage, greater magnetism, right? Greater value is created with the inductive ammeter. So what this does is this measures that magnetic field. As the flow increases, the magnetic field increases. The actual inductive ammeter senses that, and it then provides a voltage signal to your DVOM. So when you are measuring, and on this one over here, right? So let's just do this real quick. Pull these leads out. Put these leads in. All right, now, basically this is how this is going to wire up. DVOM with an inductive ammeter. All right, on this particular type of inductive ammeter, this is how it actually plugs into this particular meter. Right? Now from there, it actually says right on the inductive ammeter that 1 millivolt is equal to 1 amp. All right, so if it's 1 millivolt equals 1 amp, well then we're going to want to be on the millivolt scale. So when we go over here to voltage, we'll go to direct voltage, right? And then from there, on a direct voltage scale, we're going to select millivolts, right? Millivolts. And as that produces a voltage, we'll be able to read it there. So for example, if that says 20 millivolts, we know that that circuit is producing 20 amps of current flow. So basically this is an inductive ammeter that produces a voltage. This measures the voltage. You simply calculate the voltage in relation to the scale that's on the inductive ammeter. That's basically how it works, right? So I have multiple inductive ammeters, some more sophisticated than others, right? And then of course you have inline ammeters. Right, that is how we're going to measure amperage. Okay, plain and simple. Now the amperage is going to be a value of milliamps, amps, or kiloamps. Now it does go past that, but not in the automotive world. Right, you're never going to see 8,000 amps. It's not a thing. Right, not in the automotive world. Right, not in a low voltage DC system world or low voltage AC system. You're not going to see 1,000 amps. I mean, I never have. Right, I never have. I maybe like a big diesel, maybe starter motor that's going bad, maybe. I've never experienced it. I don't work on huge vehicles like that, like big over the road vehicles. I just don't. But in my experience, what I'm going to see is milliamps, amps, and kiloamps. Right, and a kiloamp, what I mean to say is like you will see 200 amps, which is 0.200 kiloamps. You will see 300 and 400 amps, which is 0.300 kiloamps or 0.400 kiloamps. You will see that, right? Amperage, obviously, you'll see 1 amp, 2 amps, 2.5 amps, 3 amps, whatever on the amp scale. On the milliamps, if you see 400 MA, that's 400 1,000ths or 400 over 1,000, 400 1,000ths amps or 0.400 amps. Okay, so like I said, 1/1000th, 1,000 milliamps equals 1 amp. 1,000 milliamps equals 1 amp. 1,000 amps equals 1 kiloamp. Right? 1/1000th is milli. 1,000 is kilo. 1,000,000 is mega. Right? So these are the values. This is the mathematics of it. Right? I'm not really going to get any deeper into that as far as explaining, how to do the math. It's something you're going to have to take upon yourself to learn. If you don't know, how to calculate 400 milliamps and break that down into a decimal, like 0.400, 400 milliamps is 0.400 amps. Well, it's something you're going to have to learn, right? You could probably. I don't know if there's a way around that. I think that you really need to learn what a milliamp is, or a milliohm, or a millivolt, and a kilovolt, and a kiloamp, and a kiloohm, and a mega ohm. You're going to need to understand what those are. You need to learn that. Okay. So then from there, we're going to check resistance. Resistance is quite simple to check. There's different ways of doing it, but in most instances, right, you're not going to calculate the resistance. You're going to measure the resistance. Now, you will be calculating, we'll move on to another video, and when we're doing series circuits, series parallel, and parallel circuits, you will be calculating a resistance, okay? But we're not going to be talking about that today. We're going to be talking about measuring resistance directly. So for example, if you have a light bulb, and the light bulb has two terminals, one going into the filament, one coming out of the filament, two terminals. You will take your ohm meter, put it on the ohm scale, and you will touch those two terminals just like that. And it's not polarity sensitive, right? It can be done either way on a bulb, right? So let's say you have a tungsten filament bulb, right? And you come up with whatever you come up with, right? Three ohms, whatever it might be, right? Now we'll get into that too in a later video when we get talking about checking series circuits, parallel circuits, and amperage. We're going to talk about inrush current and surge current. So maybe a bulb is not the best example for this, but nonetheless, you'll get a resistance reading from into the bulb, through the bulb, and out of the bulb. You'll get a resistance reading. That's going to be in ohms, right? So basically, checking resistance is about as simple as that. Let's say you had a fan motor, and you had a power wire going to the fan, and a ground wire or a common wire coming off the fan. One to the other, measure the two. That's the resistance in ohms. Measure it, it will show up on your meter. That resistance is your ohms. Now you've measured ohms. You measured the resistance, right? The meter has the ability to calculate it, but that's how you develop or determine that that reading, you know, that you're going to need for these calculations. So, without getting any deeper into that right at the moment, digital volt ohm meter is your best friend. You're going to have to use it. You're going to have to get comfortable with it. You're going to have to get a good one. You're going to have to read the instruction manual. You're going to have to get friendly with it. You know, you're going to have to be able to do that. It is your number one tool, right? It has to be accurate. It can't be, you know, sometimes it works, sometimes it doesn't. You got to wiggle the button, you got to wiggle the leads, whatever. If that's what you have, throw that damn thing in the garbage, right? Try to get your money back, whatever. It's got to be very accurate because sometimes we're talking about very, very low values. And if you have a poor connection inside the meter or on your leads, if it's a very, very low value, it'll skew that value, it'll skew that measurement to a point where you'll be out in left field trying to figure out what's going on. Your value is totally out of whack. You're lost. You just cannot figure out what's going on with this vehicle, this electrical circuit, because your meter's just crap, right? So make sure it's a good meter. I don't care if you pay $5 for it, your brother gives it to you, you got it from your uncle, whatever. If it's a good quality meter, it's a good quality meter. Like I said, once again, 33 years, right? And that's no lie, 33 years. It's been great. I mean, really, if I could go back, I'd buy it in a minute. Really, and it was very expensive at the time, believe me. But nonetheless, it's served me well over all these years, and it's never led me astray. The leads start acting bad. First time a lead starts giving me trouble, new set of leads. I ain't got time for that, right? I got to be sure that the readings are accurate, okay? So a good quality digital volt ohm meter, all right? 100%. So let's just touch on a few other things real quick. So before we get into all this, let's just jump down to your temperatures, all right? Because I just want to touch on that real quick. These are this right here and this one, right? And this one, right? These are called thermocouples, right? And these are actually known as what they call K-type thermocouples, right? Very common in the automotive industry, K-type, right? Thermocouples. And my meter is designed for these thermocouples to plug directly into the meter, right there, right? Got two blades, one's bigger than the other, so it only goes in one way, right? Pretty simple, plugs in. I select on my meter, I select temperature, and it reads temperature. Simple as that. So I have three different types of probes here. This one is an immersion probe, designed to go down into liquid, be submerged or immersed in whatever fluid is you're trying to test, right? It takes a little while for it to get to a steady reading because it's going to heat up slightly, right? But it's very accurate, very, very accurate. Immersion type. This is a surface probe, right? Also, like I said, a K-type thermocouple, but a surface probe. It has two little contacts right here. Make sure the surface itself is clean. Touch the two contacts together. They're spring-loaded on your surface. Wait. You get a reading value. Now you know what the surface temperature is, plain and simple. This one is an air probe, right? The probe is actually inside. It's got a housing or a shroud that goes around it to protect it, right? It measures the air around us, whether it's under the hood of a car, you know, wherever it might be, inside the interior, you know, wherever it might be. Now, things like this can come in real handy if you're doing diagnostic work, and it's getting a little off track, but let's say, for example, you're looking at a value of an interior temperature sensor. That interior temperature sensor, you know where it's located, you know, once you've found it. It says it's 147 degrees in here, which, you know, sometimes, believe it or not, depending on parts of this country, you can get that hot in there. You lay this in there next to it, right? Plug it into your meter, it should say something close to 147. If that reads 147 and this reads 92, something's wrong, right? Now you have determined that you have a problem with that sensor. This is how you're going to diagnose it, right? Just an example. You can use it for many other things besides that. But those are really handy. You don't really use them all that often. In my world, a lot of times I'll use like an infrared thermometer, which I can just actually point at it, pull a trigger, and it gives me the temperature. I use that more than I use those these days, but I still do use those. But it's very simple to explain, very easy to plug into your meter if it has that ability. It's a nice little feature to have if you're looking at a DVOM, right, digital voltometer. All right, so from there, right, we can get into, and I'm actually going to create another video talking all about engine management, tuning, things you need to know, like the values that you're seeing when you're trying to tune a car, or you're trying to program a computer system, or do something custom. There's a lot of information that you're going to be looking at that's not going to be, that you're going to have to learn. I mean, basically you have to learn the values and what they mean, and basically control and what have you, how you control circuits, using a computer system. How does the computer control injector timing? How does it control ignition timing, ignition dwell? I mean, how does the computer do that? You're going to need to learn how to change those values, read those values, determine what those values mean. So here when I have 4 through 6, these are the values I'm basically talking about. And that's going to be pulse, hertz, and duty or duty cycle. Like I said, I think that our best bet here would be to get into that in another video, because that's a very long, drawn out explanation. But so just roughly, like I said, so the DVOM itself is going to have this output. Mine says duty, and that's basically a duty cycle percentage. And mine says dwell, which is an angularity measurement measured in degrees. Of course, RPM. Nowadays, with the advent of computer systems, your RPM is going to be on your scan tool. You don't really need to actually measure the RPM. But back in the day, one of the ways you would do it is like with an inductive probe like this. This actually will go around one of the wires, right? You basically tell the voltmeter how many cylinders you're measuring. For example, like an 8-cylinder, 6-cylinder, 4-cylinder. Put this on one of the spark plug wires. It'll give you an RPM reading. It's inductive, right? Nowadays, you don't really need to even do that. As a matter of fact, a lot of cars nowadays don't even have spark plug wires, So basically, you have coil on plug ignition. It's really, you're going to have a hard time putting that around a coil on plug, right? So anyways, then of course you got your diode measurement. For years and years and years, I used to rebuild alternators. And in an alternator, you're checking the rectifier bridge and the diode trio or the triode. Used it all the time. Nowadays, when I'm wiring race cars, doing some creative circuitry, I'll use diodes. I'll put them in a system for different things, for circuit control. And for that function on the digital voltometer, I do still use that quite a bit. Not like I used to. I don't really build alternators and all that like I used to. I do rebuild the ones on my race car, because on the race car, it is still rebuildable, and I will take it apart, fix it myself, put it back together. So I still do use that on occasion. I do use it when I get creative on electrical circuits on certain types of cars. Like I said earlier, let's see here. So let's touch on real quick a couple things. So on your temperature scale, if you want to, just real quick and simple, just to bring it up, I mean, it's not really necessary for you to know this, but it's kind of interesting. If you want to find for the degrees Celsius or the degrees Fahrenheit, if you know the degree Fahrenheit and you want to find for degrees Celsius, basically just take degrees Fahrenheit minus 32, divide that by 1.8, and you'll get degrees Celsius. As an example, let's say it's 212 degrees, minus 32 is 180, 180 divided by 1.8 is 100. So 100 degrees Celsius is 212 degrees Fahrenheit. You want to find for degrees Fahrenheit, and you know the degrees Celsius. Let's say, for example, it's 0 degrees Celsius. So you're saying 0 degrees outside, 0 degrees Celsius. 0 times 1.8 is 0. 0 plus 32 is 32. So 0 degrees Celsius is 32 degrees Fahrenheit. It's very simple, the two formulas, something you can actually just remember yourself and calculate, switch from one to another. It's useful, and to me it's useful because sometimes when you're reading values on a diagnostic meter or scan tool, what have you, it might be giving you a value in degrees Celsius, which is fine. And if you're from the part of the world where you use the metric system and degrees Celsius is how you determine temperature, then it's intuitive to you. You're used to it. You know what 0 degrees Celsius is. But if you're from the United States and other countries that use degrees Fahrenheit, you're saying degrees Celsius. Okay, well, what does that mean? Like you're trying to wrap your mind around it. Well, so some very simple things. 0 degrees Celsius, 32 degrees Fahrenheit, right? 0 degrees Celsius basically just means that's the point at which water freezes. right? 100 degrees Celsius is the point at which water boils, right? Water freezes, water boils. That's why it has a value of 0, why it has a value of 100, right? It's very simple. Matter of fact, the metric system is actually much simpler than our standards of inches and feet and yards. Metric system is way simpler. Degrees Celsius compared to degrees Fahrenheit. It's actually very simple. I find it easier, but because I work on a lot of older cars, and I've been working on cars and trucks and whatever for so long, I have to know both. And I had to learn both, and over the years I had to go from standard fasteners to metric fasteners, from foot-pounds to newton meters. I mean, all of these things over the years. I had to learn all that, and I just happen to know all that now because started off knowing one and had to learn the other, and of course they intertwine. To this day they still do. So you got to know both. So anyhow, so that's just real quick on that. Temperatures degrees Celsius and degrees Fahrenheit. When you switch it on to temperature on your DVOM, you have to decide whether you're going to pick degrees Celsius or degrees Fahrenheit. You can actually change the range, right, one or the other. So basically from there, let's see here. For the older guys out there, right, the guys who still work on the old cars or have been working on cars for a long time, or motorcycles too, as a matter of fact, dwell, back in the day, what is dwell? Well, it's a measurement of degrees, and we used it back then for setting points. Right, a points condenser system, single points, dual points. You set the dwell, right? So what is dwell, right? Like I said, it's a measurement of angularity. So picture inside a distributor itself, you have, let's say it's an 8-cylinder. You're going to have a cam with 8 lobes on it. Each lobe is basically indicates one cylinder. So 8 lobes is an 8-cylinder engine. All right. So since 8 lobes go around a circle, the circle is 360 degrees. 8 lobes means that between each lobe is 45 degrees. So 360 divided by 8 lobes is 45 degrees per lobe. Okay? So an 8-cylinder engine is going to have a 45-degree duration in degrees per cylinder. Okay? So as the distributor rotates, 45 degrees, let's say cylinder 1. The next 45 degrees, cylinder 2, or 1, 8, depending on the firing order. But let's just say 1, 2, 3, 4. So first cylinder would be 45 degrees, next cylinder would be additional 45 degrees, all the way around 360 degrees until you get back to number 1. Okay? Now, on an 8-cylinder, since there's 45 degrees between each lobe, what is dwell, right? When you're setting dwell on points, what is that, right? So setting the dwell on points is the amount of time, right? So let me start over. The duration measured in degrees of distributor rotation per cylinder event that the points are closed. So let me say that again. The duration measured in degrees of distributor rotation that the points are closed. So for example, if you have a 45 degrees per cylinder on an 8-cylinder between each lobe as it's rotating, right? The lobe comes around and rubs on a contact block on the points, rubs on a contact block, and when it hits the contact block, it opens the points, breaks the circuit. Opens the circuit. So it's an electrical switch. Open, close, open, close. So it comes around, opens the circuit, then it closes the circuit. Then it opens the circuit, then it closes the circuit. Okay, that's what it does. So an 8-cylinder engine, the total available time is 45 degrees. You normally set the point dwell. The actual dwell is going to be set between 28 and 32 degrees. On a 6-cylinder, each event there'll be 6 lobes, right? So you'll have between each lobe 360 degrees divided by 6 is 60 degrees. So basically you have a total potential of 60 degrees. Normally you'll set the point somewhere between 34 and 38 degrees. On a 4-cylinder you only have 4 lobes. Those 4 lobes are going to be 90 degrees apart because it's 360 degrees divided by 4. One rotation divided by 4 is 90 degrees. Somewhere between 52 and 56 degrees. Now, like I said, this is way off of topic. I just want to touch on it real quick because I've seen posts over the years, and there's a lot of discussion about the point dwell, believe it or not, but there really is. So basically, this is down and dirty. 90 degrees times 60% is 54 degrees. So right in the middle, between 52 and 56 is 54 degrees, right? 60% of 90 degrees is 54. 60% of 60 degrees is roughly 36. It's not roughly, it is 36. 34 to 38, what's in the middle? 36, right? On an 8-cylinder, it's a little different than that, but an 8-cylinder is 45 degrees, right? 60% of that's going to be 27. So 30 degrees, which is in the middle, is going to be right around 62%, right? Wait a minute, that's wrong. 66%, I'm sorry. It's 30 degrees. 66.6% is 30 degrees. But nonetheless, usually in most cases, for example, let's say you went with the 60% rule and you set that to 27 degrees, that would work. All right. Now, that being said, that's just a rough idea of how you set the points. You're going to want to refer to the manufacturer's specifications. If you have an older model vehicle, like I said, this is a GM. I worked on hundreds of them, thousands. 28 to 32 degrees is what you would set it at, somewhere around 30 as an average. 6 cylinders, 34 to 38, set them around 36. On a 4-cylinder, 52 to 56, set it around 54. That's what we set it at. But all I'm really getting at is that it's a percentage of the close time to on time, right? So if it's, for example, if it's closed for 36, it's open for 24. 60 degree total available. Closed for 36, open 24. Closed for 30, open 15. Closed for 54, open 36. Right? That's basically what that means. All right. And one other thing I want to touch on, because I've seen a lot of controversy about this. 1 degree of dwell change is 1 degree of timing change. Plain and simple, right? Some guys will say, well, since the crankshaft rotates 2 full rotations for every 1 rotation of the distributor, that must mean that if you change the dwell 1 degree, that the ignition time is going to change 2 degrees because the crank turns twice as far, right? So, of course, that'd be 2 degrees, right? But here's what you're not thinking about. As that lobe comes around on that cam and opens the points, if I make a 2 degree change, that's 1 degree on the opening ramp and 1 degree on the closing ramp, right? So, yeah, I've changed it 2 degrees, but as the points open, that's when you fire the spark. Right, so that's where the ignition timing is going to be set at. So 2 degree change is 1 degree change at the crankshaft. A 1 degree a 1 degree change of point dwell is a half a degree open, half a degree closed. So a half a degree change here is going to be 1 degree at the crank. Okay? See what I'm saying? So 1 degree is 1 degree at the crank. But the reason that the crank turns twice as fast is because if it's 1 degree, as it comes around, it opens a half a degree sooner. 1/2 times 2 is 1. So a 1 degree change in dwell is 1 degree timing. A 2 degree change in dwell, it opens 1 degree sooner, closes 1 degree later. 1 degree of dwell difference, or actually 2 degrees, is going to be 2 at the crank because it's 1 open, 1 closed. That's why it is double. You're right. But you're not thinking about the opening event and the closing event, right? So that's the reason why they're equal 1 to 1. All right. So basically, I'm not going to get too much deeper into this right now. Like I said, with the diodes and the direction of flow through a diode and what the bands mean, what have you. I'm going to let it go at that for right now. It's getting kind of long-winded. Basically, we're going to get into this a little deeper. We're definitely going to talk more about these kinds of things. But the video is getting really long, and I'm getting off track, and we're starting to go down a rabbit hole here. So I'd like to wrap it up. I'd like to take the opportunity to thank you for listening all this time, and please do me a favor. Like, share, subscribe. This took a long time to create, and the videos in the future are going to take a long time to create. I try to make them as accurate as I possibly can. I try to put as much information into these videos as I possibly can. Like I said, it takes a lot of effort. It really doesn't pay anything. At this point, zero. It doesn't pay anything. I don't have any sponsors. I'm not sponsored by any products. Nobody's paying me to say any of this. I have no viewership. I'm not even monetized. So basically, unless I can build this channel to some degree, it's not really worth the time of doing it. I enjoy doing it, and at my age, I like to share as much as I can, while I can. So I'd like to keep doing that if I can. So do me a favor, like, share, subscribe, comment. And thank you very much for watching, and I hope to see you soon.